everybody, we are live now. So let's get started here. Points should be working, I hope, in a moment. Sometimes it takes a moment at the start of the stream. We'll see if points are working. But great job to everyone on all the points. Let me also go to Streamlabs while we do this. And so I'll make sure Streamlabs is up and running. Somehow I still think that in the background I have to be like somehow running Streamlabs. And so we will see if this helps the cloud bot. It was working yesterday. Now, something I want to point out, I'm going to show you guys something really cool here, which is something I'm definitely going to be trying out more and more. If you go to yesterday's review, let's go to yesterday's review. Something you're able to do now on YouTube, which is amazing. I'm shocked by this. And you guys are really helping out with the timestamps on here. So let me bring down this YouTube video right here. So here's the YouTube video from yesterday. And I want you to see something. Check this out, everyone. I want to see your reactions to this. Hey, what's up, Preston? Hey, Tiffany. Hey, Jeff. Feeling a little bit better. I was able to sleep last night pretty well, and my gums are doing pretty well. But thank you guys so much, Abigail and everyone. The beard is gone. I'm sorry, Logan. I got some stubble again now, so it's coming back very slowly. But feeling better. Still talking a little bit funny, but I appreciate it. Thank you guys so much for all the good stuff right there. Do you guys see this right here? If you look at it, it says conditions for regression. You go right here, formula sheet, 2 sample T hypothesis testing. If you look, you can see start of stream. So I put timestamps in the video, and now YouTube has a thing called chapters. So you can actually put these in. I have to manually enter them in. But when you hover over the part of the video, you can see what we're covering for this part of the video. So it literally shows you this is the start of the stream where I was talking about everything, and then you can actually see in the video I'm doing it. But what do you guys think of that? Do you guys think that's a pretty cool feature that you can actually hover over it and see what's going on? I know, I think it's awesome too. I'm really excited about it. It's something that just got rolled out this month. Eat slices of lemon. Or I might try that out. Who knows? So I don't know. My gums are ripped up. They ripped into my gums a little bit. So I don't know. Are lemons supposed to be good? I'm just having like yogurt. So I know. And so if you guys keep using timestamps, I'll keep trying to put them in here. I did in another video, so there's a future thing going forward. But you could literally click the timestamps as per usual. So you can see yesterday's video. And then you can see everything right here, like when I start the next topic. Like it literally has a break. You can see how it like highlights the video. So I think it's really cool. Email me, just email me, Logan, if you're maxed out. Awesome stuff right here. So I think it's super helpful too. I'm always looking to improve this. And you guys know I love tech. So when we figure out better ways of doing stuff, we just do better and better and better ways. So you guys keep telling me what you like, what you don't like, and I'll keep trying to do that. I think the audio seems to be pretty good today. Yep, right there. How do you know if you're maxed out? I maxed you out in class. There's a lot of ways to get maxed out. You can do all the homework and the quizzes. You can get a bunch of points, but we were maxing out people during class to get them extra credit. And so make sure to email me extra credit. Make sure to enter it in. I'll be adding it all up. Lots going on. A lot of people are near the max. My goal was, as I said, to max out as many people as we can. I wanted to max out as many students as I could. Still talking a tiny bit funny. So I'll get used to it. And so today starts some new topics. I was going to start today by doing all the output. Would you guys like to see all the different output? How does that sound? I got to make sure not to close. I can't close my mouth completely because that's when it hurts a little bit. So I'm like talking without closing my mouth, which is a hard thing to do. Sounds good. Let's do that. Okay. So we are going to do all the different output you could do in Jump and talk about how to read it. So let's start with a 1 sample proportion test. So I need to know in the chat, so this part of the video will be labeled 1 sample proportion. I should do things like this. Sometimes people do things where they like put their hands up so they can mark the spot in the video. So right now we're doing the 1 sample proportion test. And so the 1 sample proportion test is when you have what type of variable? 1 sample proportion test is what type of variable? 1 sample proportion test is what type of variable? Who knows? 1 sample proportion test. I can do it on this data right here. What kind of data is a 1 sample? You got it, Julio, right there, categorical. And if you look, we can do it on this one or this one. We can do 1 sample proportion test on either of these. So let's go here to analyze distribution. And let's go here to payment method. Okay, we're going to do a 1 sample proportion test on this. So I'm going to stack it, just makes it look nicer. That's the only reason I do it. I just like reading left to right, not up and down. Good to see you here, Benjamin. And we are now going to go to tests, probabilities, and we can do it. Now this one does it a little bit differently. Actually, so we don't usually show you this jump output, but I'll show it anyways. And so here, it's doing it with the chi-squared, so this won't be on the test. But let's see the other output that will be on the test. So I'm going to remove this one. I guess I might have to actually totally remove it. That one does a chi-squared test. There's multiple ways to do tests. You'd be shocked. There's a lot of statistical tests that can be used to do the same thing. That will not be on the test. We're doing card, not card. Let's do the confidence interval that will be on the test, or could be on the test, I should say. So once again, this is a one sample proportion confidence interval. And let's go here to confidence interval, and let's go to 95. Okay, so this looks a lot like your project right here, and let's bring it over into Word and talk about what all this output is. Let's make notations on it and make sure we know every last bit of output and interpret it. So here's all of our output, and we're going to paste it right into here. We're going to zoom in a good bit, and we're going to start marking on it so we know what's going on right here. Hey, what's up, Joel? What do we have right here with this right here? Can anyone interpret this for me right here and what value that is? What is that value right there? What is value number 1? Start figuring out what these values are. We'll call this value 1, call this value 2, and we'll call this value 3, call this value 4, and this will be value 5 right here. So does anyone have any idea? Probability of paying with a card, you were right, so we could call this P hat right here. That is the sample proportion of people who paid with a card. Out of our sample, there was 54.3% of people who paid with a card. This right here is going to be the count of how many people paid with a card. So this is actually, you know what's funny about this? This is actually X right here. There we go. That is actually X. Now, 4 is going to be a weird one when we get to 4. 54% of people paid with the card, you are right, is P hat, the percent of people who paid with the card. And then we have 3. Great job, everybody. 3 is going to be Q hat right here. So that's the third one right there is Q hat. Does anyone have any idea on the other ones? Everyone should know number 5. Number 5 is what in the output? Number 5 is what? Everyone should know that one really quickly. Make sure not to capitalize it. You got it right, Walker. 5 is N. There we go right there. Capital N is actually population size. It could be a population, but lowercase n is sample size. Very minute difference right there. I wouldn't care so much on a test. It's like, okay, you know it's sample size. So, I mean, it's not that big of a deal. 4 is a weird one. 4 is n minus x. You can confirm this. Can anyone solve for me in their head what 126 or 232 minus 126 is? So 232 minus 126. Can anyone figure out what that is in their head? 106, you're right. It's 106. So you can confirm that that is basically the ones that do not conform. Because when you think about this, how would you interpret this 106 in words? How would you just say to someone what this 106 is in words? That 106 in words, well, a weird way to say it is everyone who did not pay with card paid with cash. So you're basically doing everyone who did not pay with card. So you're doing the remaining amount of people. So if we call the other one X, the other one is N minus X, because this, you think if you add X to this, you get N. So there's a lot of ways to look at this, but that number right there is everyone who paid with card, and it would be everybody but those who paid with card. So I might have reversed it, but that's everyone who paid with cash. I think I just made one error. So we know what all this is. We go over to the confidence intervals, which is going to be super important for the test. We see the lower bound on the confidence interval and the upper bound on the confidence interval. Now, both of these are confidence intervals because you could consider P had a confidence interval or Q had a confidence interval. But let's take a look at the equations for this. So the equation for this right here, to make any of these confidence intervals, is P hat plus or minus Z star P hat times Q hat over N square root. So if you notice, we have basically everything we need right here. We have Q hat, we have P hat, we have N. We can tell you what Z is. Does anyone know what Z would be for a 95% confidence interval? What is Z for a 95% confidence interval? Who knows that answer? I'll try to erase this highlighter right here. Who knows what Z for a 95% confidence interval is? Really? There we go. Who knows Z for a 95% confidence interval? Why is card X? Could you... it's interchangeable. Card can be X or cash can be X. It's just depending on which one you want to talk about. Usually P hat is the one we want to make a confidence interval for, so you could reverse it and make cash X, and then talk about let's make a confidence interval for those who pay with cash, and then the amount who paid in cash would be X, and the proportion of who paid in cash would be X over N. Does that make sense, Katie? It's like one of them will be X and the other will be N minus X. I'm 95% confident the true proportion of people paid with cards contained in the interval. Perfect. That is a perfect interpretation right there. I am 95% confident that the true proportion of people who paid with card. If you notice when we started this question, it was all about the proportion of people paying with a card because it's categorical. And everyone remembered that 1.96, you don't need to have that memorized, but 1.96 is the z-score for a 95% confidence interval. So this alpha level right here tells you the percent of confidence. It relates to the normal curve that right now we are shading 95% of the normal curve. Keep asking questions, you guys got them. And thank you guys so much for being here and asking questions. This is we're trying to do as much review as we can. I'll zoom out a tiny bit, that'll help. There we go. So when we make this interval, we go from here to here, and then that's a 95% confidence interval, which goes from negative 1.96 to 1.96, which is the value used right in here. So that value that we obtain is the z-score for it. The z-score tells us the percent confidence. Yeah, that'd be like how many people pay with card. How many people pay with card is 126. How many people pay with cash is 106. And then the percentages are over there. Does all of this output make sense? Who feels like they understand this output a little bit better now? I can highlight just a little bit more since we want to talk about everything in this output. But that thing right there just tells you the percent confidence which is related to the z-score. This is how many people pay with card. This is how many people pay with cash. This is the total amount of people. So we see here X, N minus X, and N again. And this is the P hat. This is Q hat. And then we have the lower bound for one of the intervals and the upper bound, and then the lower bound and the upper bound. Like I am blank percent confident that the true blank is contained in the interval blank to blank. So this is probably one of the easiest outputs, I think. We're going to do some more complicated ones. Are we given? Yes, you will be given that. Yay. What's up, Abby? You will be given it. And you will be giving Z's on the test. You will be given Z's. So some classic Z's that you could be given. I need to get the new microphone stand so I can talk more like this. Some Z-scores that are very classic. Let's put the Z here. And you don't need to memorize these. But very classic Z-scores you guys have probably seen are like 80% is 1.2818. Oh, no, it's 6. I just remembered that. I used to get that wrong. You got to know it's 4 decimals. And then 90% is 1.6449, if you're going to do 4 decimals. 95 is 1.96, or 1.9559. No, I can't remember the decimals on that one. And then things like 98, which I can't write today. You do not need to memorize these. But I want to show you something about these. What do you notice? Question 9, time practice. Yep, we can do it next year. We'll do that as the next problem. What do you notice about these z-scores as you get more confident? What do you notice about the z-scores as you get more confident? Can anyone give me, as I go and get the practice test right here, can anyone tell me they get bigger? You're right. So the z-score relates to the percent confidence. So as you get more confident, the z-score gets bigger. So it directly relates right here. Directly relates to it. Directly relates to it. So let's go grab that practice test. Some people are wanting that, and since you guys are here, you guys get to direct the conversation. So we'll do more output here in a moment. I want to do all the output I can today to show it. And I showed off the cool timestamp stuff, which I'm really excited about. Review material. And we need to go to the practice test. Of course, it's a PDF. We'll just copy it. So here we are right here. Here's the practice test. Number 9 and 10 was it? I think those might be tools and techniques. I do like tools and techniques. So the more confident are we, less precise. Exactly. So as you go more confident, you get less precise because your interval gets wider. What does the margin of error, when does the margin of error get smaller? Just briefly to go over that real quick. We'll finish this one off. Margin of error gets smaller in 2 ways, really. The 2 ways the margin of error gets smaller, let's look at the formula. The 2 ways the margin of error gets smaller what are the 2? You got Julio's got one of them. And we can do true false too. Larger sample size. And I will point out there's a playlist where I go through the videos. Does anyone know about? I'm going to do them here still. I don't want people to think I won't do them. But there is a playlist where I go through the videos. Oh, I'll do that in a moment here, Walker. We'll do 9 and 10, then we'll do yours right there. We'll do true false. 9, 10, true false, and then Walker's question. So the one thing Julio points out right here is a larger sample size. That'll make the margin of error smaller. Everything right here is the margin of error. And then, well, alpha is related to tests. It's similar to a confidence interval, but so I see what you're saying. Sarah, you're basically right. You could, if you want to make the margin of error smaller, it would actually relate to a bigger alpha, but we would say to make the margin of error smaller, you would choose a smaller z. And so that relates to what I have right here, because look at these values of z right here. Whoops. Oh my gosh, I reversed my numbers. That's what I get. This is the z. That's the percent. So as you go up in percent, so if you wanted to make it smaller, you'd have to go down because these are the numbers that go here. So when you choose a smaller percent, you have a smaller margin of error. So if you want a smaller margin of error, it actually relate to a larger alpha. Does that make sense there, Sarah? That your percent confidence relates to how big your margin of error is. So this whole thing right here is the margin of error. And your percent confidence, you got it. Nice job. Great job, Sarah. Let's look at 9 and 10 right here. So 9 and 10. What do we got 9 and 10? And are you guys talking about which ones? Which ones are 9 and 10? Sorry, we put tests together to make this. Oh, here we go. Okay, cool. They are tools and techniques. Let me grab the tools and techniques and explain through. Good questions. Tools and techniques stuff definitely trip people up. And let's hop here. Okay. So the tools and techniques one's right here. Here's what I would do immediately when you get to these. Immediately when you get to these, we're going to start labeling these. Here's the number one trick for tools and techniques. Is everyone ready? I want to hear some people who are ready in the chat. If you're ready, hit that like button. It's my way to get people to hit like. Who's ready in the chat? Tell me how many likes there are. Who is ready? Well, you can say you're ready too, because I'm not looking at the likes right now. Who is ready? Anyone ready? No one's ready? You're ready? Great job, Ava. Let's do this. Okay. I got it. Brian's ready too. I'm ready. I'm ready. You guys know what I'm talking about. So let's go here and let's make some notes. A box plot is for how many types of variables? A box plot is for how many types of variables? Thank you, Brian. Kind of. Julio, you're kind of right. But wait a minute. A box plot. A box plot. I'll draw a box plot on here. A box plot looks like this. A box plot is for how many types of variables? One variable, and that one variable is what? I see where you guys are going with two box plots, but we're not there yet. It's for one what type of variable? You're right, quantitative. Good. That is one quantitative variable. Like that could measure, a box plot can look at heights, weights, GPAs. Box plots and histograms go together, so make a note, box plots and histograms analyze the same type of data. We have a hypothesis test for a population mean. So a hypothesis test for a population mean would be for what kind of data? For a hypothesis test, it would be how many types of variables and what kind of variable. We got a tricky one coming next. Hint. One quantitative. You're right, Rachel. Nice job. Okay. And then decision tree right here. A decision tree, I'll just answer this one, handles a lot of variables. Lots of vars. If you remember from decision trees, we just dump in all the variables. So a decision tree problem would be like Amazon is trying to make selling decisions to their customers, and they have data on 50 different variables to predict what their customers want to buy. What would you use to maybe, analyze and make predictions? I would say a decision tree or something like that. It can take tons of variables. A box plot would be like, let's make a visualization of someone's height. Let's make a visualization of someone's weight. A hypothesis test for a population mean would be, let's test people's heights. Let's test people's weight. And do you notice how when I said let's make a visualization for people's heights or weights, it's one quantitative. When I say let's test people's heights or weights, it's one quantitative. The Amazon question, when they want to make predictions to sell their customers, basically has a lot of variables and we're making decisions on it. So we're using lots and lots and lots and lots of data to make predictions. Confidence interval for difference between two population means. Now, this is what you were thinking of with the two box plots. This one has what two types of variables? Confidence interval for the difference between two population means. What two types of variables? What two types of variables would this have? So we have two populations, and we're going to look at the means between them. You guys are close. I don't see the answer yet in the chat. We have two populations. Pause the video, try to answer these as I'm doing them, see if you can memorize them. We might have the right answer. I need someone to tell me fully what the right answer is. We're getting close. Yes, Walker, you're right. It is two quantitative variables. I mean, oh my gosh. I was looking at the next one as I said it. It is a quantitative and categorical. If you said I did say Walker is right. It's a quant and a categorical. Specifically, we'll have the green pen. This one is the Y, and this one is the X. So it's very specific right there. But I already see people saying two quantitative variables. When you have two quantitative variables, you're either making a scatter plot visually or you're doing what? When you have two quantitative variables, you're making a scatter plot or you're doing this. When you have two quantitative variables, QQ, straight enough, no outliers, plot doesn't thicken. When you have two quantitative variables, you're making a scatter plot or doing this. You can make a scatter plot if you want, or you could do this type of statistical test. Regression, you're right. So the last one here is that. And of course, the Y and X are Y is quantitative and X is quantitative. So let's see here. Does studying really pay off? Is there a relationship between number of minutes students spent studying for exam 3? So this is number of minutes. Number of minutes is a what type of variable? Number of minutes is a what type of variable? Number of minutes is a what type of variable? Who knows? Number of minutes. It's quantitative. And their average score. Their average score is what here? Their average score is what type of variable? Their average score is, I think, I'll let you guys because same answer. So what's the answer? What is the answer to the question? Is A, B, C, D, or E? Is the answer to the question A, B, C, D, or E? It is E. We figured it out. Now, here's where you can really test yourself. Can anyone in the chat, I want everyone, we got, how many, I don't know how many people we have watching right now. I'm going to cheat. I'm going to look. Do we have 30? Do we have 40? Do we have 10? Let's see how many people we got watching. You can put stuff on there to tell you how many people are watching. There are 40. We're good. Nice. I like that. I want you guys in the chat right now, I want you to make up a question. So I want you to make up a question using what we have on the screen right here. We'll go back to it. That would be A, B, C, D, or E. And I'm going to answer, I want you guys to make up a fake question. Let's take a moment here. Let's all work together. And I want you guys to make up a question in the chat. Like, here, I'll make up one. You ready? Brian wants to see if the average GPA of students is higher than 3.5. Now, don't use mine because you can change that. Brian wants to see if the average weight of students is above 140. Brian wants to see if the average height of students is above 150. I don't know. But if you yep, Walker's got it. That is B. That's a hypothesis test on a quantitative variable. Can anyone here write a question for us? I might come up with one more. Try writing a question right now that meets one of these things right here that you would use and see if you can come up with a question yourself. That's when you really know it. If you can make up your own questions that meet one of these guidelines, you know how to identify it. And that's the real key to learning. It's like when you can come up with questions, you'll be like, oh, well, I could come up with this question here. And that's all we're doing when we write tests. We just make up questions ourselves. So I'll come up with another one, see if we can get some people to do some ones in the chat. Brian wants to see if students learn better online or in class. Brian wants to see if students learn better online or in class. So he takes the grades of the online class and compares them to the in-class class. Brian wants to see if students work better online or in class. So UT wants to see if students in Greek life have a GPA. Yep, that would be a B question. Nice job there, Campbell. That'd be a B right there because we're testing a quantitative value. We're testing it, we're hypothesizing 3.0. 3.0 would be the null value. That'd be the mu naught. And Walker's right, that would be D because I want to compare two groups. When you heard me say the online or the in-class students, that's the categorical variable. And then when you heard me say that we're going to compare the GPAs of them, that was the quantitative variable. So those key things right there. Brian wants to compare the GPAs, because that's what I'm going to look at, of online or in-class students. And so Smokies wants to see how many days it's rained this spring. And then make sure you want to do like an average. Or Smokies, so I'm going to change that lightly, Katie, right there. Great thing right there. Great question. Smokies wants to see if it's rained more than a quarter of the time. Now, that one's not on here. Let's look if it's on the next set. It is. Wait. Okay, no, it's not. I thought I saw it. I just mislooked. Smokies wants to see if it's rained more than a quarter of the days. So what would that be? That would be a hypothesis test. We'll add it in right here. Can I go below this? May I? Here we go. That one would be choice. Go back. F. And choice F right here is going to be hypothesis test on the true, or for the either which way. But Smokies wants to see if it's rained more than 25% of the days. And 25% of the days would be P naught, because that's what we're hypothesizing. So if you think about how this is done, the question would just be Smokies wants to see how much it's been raining this semester. So they take a sample of days and try to figure out if it's rained more than 25% of days. So they're testing the true proportion. Does everyone see this right here? That would be, and great job there, Katie. Excellent work. What do we have right here? We have another set of things. I need to know what a histogram can be used for. What kind of data can a histogram be made from? What kind of data can a histogram be made from? Any ideas on what data can make a histogram? Any ideas? One quantitative, you're right. Chi-squared has a special condition called count data. The chi-squared test of independence has a special condition called count data. What is that? What does that mean? You guys are on it. Nice job. There's a little histogram. Simple linear regression is quantitative. Quantitative, we just did that one earlier. Doesn't look like a cube. Oh no, why you do that? You weren't doing that every time. And correlation is basically the same. Hypothesis test is a little hard to draw. This graphic goes with these two right here. So that graphic of correlation and regression are very similar. Hypothesis test for a mean is when you have one quantitative variable. There we go. So does everyone understand what I've done right here? I've made marks to know which ones to use and when, and then we just have to figure out what's going on with this. Does everyone understand that I'm just figuring out the variable types that'll be used in these types of questions? I've got a little kind of mini graphic over there for some of them. C and E are the same graphic because correlation and regression, we do them with scatter plots. So C and E is just a scatter plot. I'll draw a bigger version of it. Just draw this. This is just a fake scatter plot. You do this, and then you put these in here like this, little dots. So that's what that graphic is, and that is C and E. So hopefully everyone understands what's going on right there. And Rex, you are right. Well, kind of. You guys are thinking of the expected cell count. The condition is count data, which means they need to be categorical. So there is expected cell count. You are very right. That is a condition of the chi-squared test of independence. But the condition count data means it needs to be two categorical variables. Is everyone clear on that? The condition, and we did this yesterday. I've got it and pull it up. Nice job and great questions in the chat. And I did post this. Thank you for those who want me to post this. This is now posted with my horrible handwriting on it. Count data means two categorical variables, and you're thinking expected cell count greater than 5. I had the highlighter, and that went away. So that's the conditions you were thinking of right here for the chi-squared test of independence. So excellent work right there. And so let's read the question now. We're ready to read the question. You are the regional manager of 5 local grocery stores. You let the manager of these 5 stores make decisions on who to hire. Since the 5 stores are within 50 miles of each other, this is all just fluff, you would expect the ethnic backgrounds of the employees at the 5 stores to be very similar. Is this the case? What would you use to look at this? So we've got right here the ethnic background. Now the highlighter wants to do its thing. You've got right here the ethnic background, and you've got right here the 5 stores. So what kind of variable is store A, store B, store C, store D, store E? What kind of variable is like the store that's on Clinton Highway, the store that's on Cumberland? What kind of variable would that be? Categorical, you're right. because it's not quantitative. It's just a category. It's like store A, store B. It's not a real number. What kind of variable is ethnic background? Is that quantity when you say what's your ethnic background? Someone says 50. Is that how it works? You bet. You guys got it. Categorical. So what's the answer here? Since these are both categorical variables, what do we have? I think you guys got it. It's highlighted right now. The answer is highlighted. Chi-square test of independence. If it said you wanted to make a visualization with this, what visualization could you make? So I kind of hinted at this already. What kind of visualization could you make with this? If it was like they want to visualize their data, what could you do? If they wanted to visualize their data, what could they do? Mosaic, you're right. There it is. There's the mosaic, or contingency table, I should say too. But mosaic plot or contingency table, which I've drawn a little mosaic plot over there, just a little miniature mosaic plot. It's got where the bars, it looks like a square. So how do you make a square? I can't make a square. And so that's got it. Does everyone understand these a little bit better? Hypothesis test for the true proportion is categorical, and so that's to see if the true proportion is a certain value right there. So I said on, maybe I should say for. We can argue over the right word. But does everyone understand that'd be one categorical variable and we have a lot? This helped a lot. That's awesome. Just make sure that was helpful. Good. I like that. You guys always direct the reviews. You guys ask the questions. And then knowing how to solve problems, I think, is really key. So great stuff right there. Excellent work. We'll put our hands up. Another segment right here. So I can usually tell when I go through the video and try to find stuff too. And I do want to point out again, I think I pointed out right here. In the previous videos, I now have a thing where I can add segments. So you can see when I hover over it, if you look right above this, it says formula sheet for review. So you can literally see like what I'm doing in each part. So if you didn't see this earlier, you can see start of stream, conditions for regression, and I went through and did this last night, formula sheet for review, and I'm going to try to do this to more videos. And thank you for people who leave timestamps. Once again, I want to say this real quick. There's a quick advert right here. One of the best ways to help the channel is to like any video you watch. Anytime you're on a video, if you just go here and click that like button, that's a huge help to the videos. Also, commenting underneath videos. If you go underneath a video and add a comment down in the comment section, that also helps videos. We're just trying to get as much reach with our videos as we can. We get people from other universities who watch these, and I want to make as much content as we can and get this as far out there as we can. So if you see a video and if you hit like on it, that's a huge help. If you throw a comment underneath it, even your comments like, I'm really glad, this and this. That's actually not that bad, Walker. I'll watch some videos that like 500 people are watching live and there'll be like 50 likes. So thank you guys for every like. Don't worry, if you don't like it, you can hit dislike. That's all right. Go here. Go dislike. Dislike my own video. I'm not going to dislike my own video. Apparently, interaction is interaction. But I thank you guys for being here. Let's do the true falses now. I think you guys wanted true false, right? True false is always fun. And true false is going to be on this test. So let's do the true falses. And then I think Walker had a question after this too. So, and I will say this, it's literally you guys who make the channel. That's why I'm always up for doing what you guys want. And I really appreciate so many people have been so supportive. The university's been so supportive. So thank you guys. I know everyone's always like, thank you so much. But really, if you guys stop watching the videos, then the channel doesn't get, you guys could be like, I don't want to watch YouTube. I don't like the brands of stuff on YouTube. I like it. I like seeing you guys like Ava right there in the chat and Walker. It's really easy to talk to you guys. Yep. Where are the max extra credit problems again? They are in that playlist. Double check the new link, Rex. There's a new link that has the right playlist. It's like right playlist for max extra credit. You'll see it. Go to it. Watch the videos. Record the problems. Practice them. And that's my goal with that. My goal is that you practice problems and know how to do certain versions of them. So I think it'll be a big help right there. So I think I'll drop that in the, we don't want to lose people yet. If you want a good set of videos to watch after this that goes through all the different problems, I'll drop it in the chat here. And then we'll do the true falses. Where is it? I keep grabbing the wrong playlist. Here it is right here. I got it. Let's go back to the chat. Here is the playlist right here. That is the playlist. Don't leave this video yet. Just maybe right click on it, new tab. And it goes through a lot of the stuff I'm going through today. So you can do it another time. We're just going to keep going. Here we go. Power represents the probability that we correctly fail to reject a true null hypothesis. That is all kinds of wrong. It's in one of the videos. I can do that today, Katie. We'll put that on the list next after all this. We'll do true falses, Walker question, then we'll do that next. So I can do all the nulls and alternatives next, and then I'll be able to timestamp in the video. Power represents the probability that we correctly reject a true null hypothesis. If the null is true and you reject it, what have you done? So everyone, I want you to think about this. If the null is true and you reject it, what have you done? If the null is true, what have you done? Type 1 error, that's it. This is not power, this is a type 1 error. Because in a type 1 error, the null is true, and it says we correctly failed to reject a true null hypothesis. Actually, I stand corrected. It's so weirdly worded. One, I'll tell you it's not power right away, but this says we correctly fail to reject a true null, which is what you should do to the null. That's the right decision, but that's not power. Power is the ability to reject the false null. Power is the ability to reject the false null. Let me take this over to Word so I can write on it. Power is the ability to correctly reject the false null hypothesis. So power is the ability, I'll say it one more time, I'm writing it up, is the ability to correctly reject the false null. When you reject the true null, that's a type 1. Lots of good things going on right here. But let's slow this down. Power is 1 minus beta. You must know what alpha and beta are. Here's how you remember what alpha and beta are. 1, 2, A, B, plus, minus. So alpha is a what? Alpha is a type what error? Alpha is your type what error rate? Alpha is your type what error rate? I think you used my cheat sheet. You're right. Alpha is your type 1, and beta is your type 2. So when you see 1 minus beta, power is not making type 2 errors. So a type 2 is when the null is false. There's the 2 and there's the false, and we fail to reject it. So this might be something you just have to memorize, put it on a flashcard. Power is the ability to correctly reject the false null. Let me write that out here so everyone can see. I'll put it in the chat. So power is the ability to correctly reject the false null. Basically, power is being able to find results. Because if you make a type 2 error, you fail to reject the false null, fail to reject false null type 2. And so a type 2 error means there was results, but you didn't find them. So a powerful test does not make a type 2 error. So when I stand corrected, this is 100% false, but this would be a test making a right decision, because if we fail to reject a true null, that's what we should do. If the null is true, you should fail to reject it. A type 1 error is rejecting the true null. A type 2 error is failing to reject a false null. A lot going on right there. That is like flashcard material. And so we just did a big mega review of a thing I do in like 20 minutes over class. We did in like 2-3 minutes. But this one is definitely false. If based on the same set of data, you change your level of confidence from 90 to 95. So who knows what I'm going to do with my hands when I say 90 to 95. When I say 90 to 95, what are my hands going to do? You see me do this a lot. And it's one of the best ways to know it. When I say 90 to 95, I'm going to go 90, and then what's going to my 95? Go further apart. I'm going to say 95. So I'm going to say 90 to 95. So we got a wider interval. The resulting confidence interval is going to be less precise. So think about a precise measurement. Precise is like when you say dinner's going to cost between $20 to $21. That's very precise. But then a non-precise measurement would be like dinner's going to cost between $20 to $30. Everyone here, as my interval got less precise. Precise is like a very narrow field. This is very precise. But then if we widen it, because we're getting more confident, it'd be less precise. So this one right here, it's going to be less precise. The resulting 95% confidence interval is considered less precise. That is true. And so this is very true right here. Because when you go from a 90, thank you, Jillian, right there. When you go from a 90 to a 95, you include more values, it's less precise. It's like, once again, saying dinner will cost $20 to $21. Dinner is going to cost $19 to $30. It's less precise. Be like, can you give me a more precise guess on this? A more precise measurement? Thank you, Campbell. A p-value represents the probability of seeing your results, or results more unusual than that, assuming the null is true. So knock at my door. It's probably just Amazon delivering. I'll be right back, everyone. 2 moments. You guys are awesome. I'm pretty sure it was Amazon. You guys probably just heard me say hello. I didn't mute the mic. I was like, I'll just turn off my video for a second. Yeah, we can do that here after this, Abby. So a p-value represents the probability of our results or results from our stream happening by random chance, given that the null is true. That's a very true definition. Now, I said what I usually say. This right here has everything in line. There's nothing wrong with this. So I will say this. Once again, I always say the p-value is the probability of our results or results from our stream happening by random chance variation, given that the null is true. People laugh them sometimes because I'm like, the p-value is the probability of our results or results from our stream happening by random chance variation, given that the null is true. And I'm like, yeah, it's my first time saying that. Totally promise you. Well, it's the third time I've said it 3 times today. So that's the third time I've ever said that. But this has everything I want in this. It says the p-value represents the probability of seeing the results you saw, my results, or results more unusual than that, assuming that the null is true. Yes. So let's go down to here and let's draw what the p-value looks like. Here's what the p-value looks like. We draw a curve, and then we put right here, so we'll put a little thing for this one. This is this question. What is at the center of this curve? What value is always at the center of this curve? Does anyone know what value? It's in the wording up here. What value is at the center of this curve that we assume is true? That we're saying, like, this is what we'd likely to see. Does anyone know what value will go at the center of this curve? It's the thing we think is true. Kind of. You're kind of right. You're very close, Sarah. It could be a mean. Here's the things it can be. It can be mu naught. You know what it can also be? It's going to do that to me. It can be p naught. It can be mu naught. There we go. You guys got it. It's the null value. So this is the hypothesized value. It can be the hypothesized mean. It can be the hypothesized proportion. So this is the null value right here. So this is basically what is true according to the null. Does that make sense? Think about this. If the null is true, then the null would go at the center of the curve because that's the most likely thing to see. Because think if I throw a dart at this, the most likely thing to hit would be the middle of the curve. Somewhere around the middle, the least likely parts would be towards the tails. So what else do we get right here? We see a p-value represents the probability of our results. So we have to draw a line right here. And we draw a line where our results would be. So this is our results. And then we need to draw results more extreme than this. If I'm doing a greater than test, more extreme would be to the what of my results. If I'm doing a greater than test, the more extreme would be to the where of my result. I'm doing a greater than alternative to the right. So let's look. This right here that is the p-value. And let's see everything. The p-value right here is the probability. So it's a percent on the curve. The p-value represents a probability. So let's do that. Probability of my results, which is right here, or results more extreme than that. So it's more extreme than this line, given the null is true. The probability of my results or results more extreme, given the null is true. So everything you see in the definition right there is the representation of a p-value. This is a very, 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 very true statement. If you notice right here, if you were to land, when would you get the biggest p-values? When would you get the biggest p-values? Like if I did another test, like a whole nother test right here, I'm going to get a cool new pen. We're going to go rainbow pen because rainbow pen's awesome. It's making a return right now. If we were to get the biggest p-values, we'd land, you're right, Abby, excellent work. We'd land very close to the middle. Is that rainbow pen? Doesn't look like rainbow pen. I'll trust them. So here we can test. Yeah, it's rainbow pen. So right here we see the p-value for this one would be something like this right here. And think about this. With this result, so we'll draw this out. Your p-value would now be very what? Very large or small? Would your p-value be very large or small if you landed right on the null? If you land right on their null, your p-value would be very large or small. What do you guys think? I mean, look at it. It'd be very large. And since the p-value is large, you would do what to the null? You would reject it or fail to reject it. If you land right on the null, do you think, like you're saying, I think the average GPA of students is 3.8, and then you observe 3.8. You would fail to reject. And think about this just theoretically. This right here, you saw in your sample what you thought you would see according to the null. So you observed what you expected. So you'd be like, well, I don't reject it because this was very likely given the null is true. The p-value tells you how likely or unlikely your results are. This one might not be small enough, but in this instance, this result right here was more unlikely. And you could do things to make it more and more unlikely by just going further away. So the further away we are over, usually by z-scores or t-scores, the less area under the curve, telling us the less probable what we saw was, given the null is true. So this p-value right here tells us how probable was your results or results more extreme, given the null right there is true. Does that make a little more sense to anybody? I think once you hear the p-value thing about 20 times, you're like, starting to make sense to me. Starting to make sense why we use this in statistics to tell us if what we saw in our sample was likely or unlikely, given the null is true. And that's why we start out believing the null till we have evidence from our sample that the null is not true for an alternative. And this will be greater than. Hopefully that's a really good review of p-values right there, and hopefully that helps people understand how we use p-values in statistics. The only way to decrease the probability of a type 2 error is to increase the probability of a type 1 error. Nope. There are 3 things that go into a type 2 error. The 3 things that go into a type 2 error are going to be sample size, alpha, and effect size. These are the 3 things right here that go into a type 2 error. So if you notice, one of them is a type 1 error. That is a type 1 error. The type 1 error does augment the type 2 error. If you increase your type 1 error, you decrease your type 2 error. So, these all have inverse relationships. If you increase your sample size, you decrease your type 2 error. So if any of these go up, type 2 goes down. Effect size is the difference between the null and the truth. So I always like to use an example where I say I play my brother in basketball, or I play LeBron in basketball. Which of those do you think would be easier? It's classic. People have heard me say this 1,000 times now. But which of these do you think would be easier to see who's better? Me versus LeBron or me versus my brother? Me versus LeBron or me versus my brother? Which of those is going to be easier to see who's better? Probably versus LeBron. He's probably way better than me. So the truth is that LeBron is way better. The truth is that my brother's better, but there's a bigger effect size between me and LeBron. Between me and LeBron, LeBron's like way better. So that's the effect size you're seeing right there. I always do this too. Great times during the COVID pandemic to mention this. I like doing this one in person, but I can't do it today. But imagine if you go into the emergency room and you're like, I'm sick, and you have a cough, and you're like, I'll say this. I've done this for so many semesters, now it's so relevant. But you go into the emergency room and you're like, I'm sick. I'm sick. But imagine if you go into the emergency room and you go in and they just wheel you in on a stretcher and they're like, there's a major problem here. We think something's going on. In one of them, the effect size is much larger. So what you'll notice is the first person might be sick with the cough, but the effect size is very small. Like they are sick, but it's harder to detect. In the second one, they're way more sick and it's way easier to detect. Because think about this. In a type 2 error, what would they do to a sick person? In a type 2 error, what would happen to a sick person? A type 2 error, what would happen to a sick person? I love it when people are saying hey to each other in chat. Do not worry. Say hey to each other. I love that. I want you guys got your community right here. So hey, say hey to each other. Tell them they're fine when they're not. You got it, Sarah. We are on a social media platform, so I want you guys to treat this like one. I mean, be respectful, obviously. I mean, you guys are, but... So, bingo. Julian said it really good statistically. They would fail to reject that they are sick. In a type 2, the null is what? In a type 2, the null is what? In a type 2, the null is this. In type 2, the null is false. So it is false that they are not sick. But we are going to fail to reject that. Now, it's false that they are not sick, so they are actually sick. But we are going to fail to reject the null and say that they are not sick. No, it's going to be an error when we fail to reject the null. If it ever confuses you, like, what are they actually? Be like, wait, we fail to reject the null and this is an error. So if this is an error to say they are not sick, they're actually sick. Does that make sense to everybody right there? In a type 1, the null is true, but we reject it. So the null is true. You might think your doctor is amazing if you get a type 1 error. You'd be like, wow, I went in, I had all these problems. They gave me medicine. 2 days later, I felt excellent. But if that was a type 1 error, what really happened? So you say, man, I went to my doctor. I was feeling a little out of it. And they were like, here, take this medicine. They call it, it started like a pla and C. I think it was placebo, they said. It was some brand. I don't know the placebo brand, but they gave me a placebo. I tell you, 2 days later, I felt amazing. Exactly. So you get the joke right there. Placebos are sugar pills. They don't do anything to you. So a type 1 error is when the null is true. In a type 1, the null is true, but we reject it. In a type 1, the null is true, so it is true you are not sick, but they reject it and say you are sick. Now, of course, if they give you a placebo, they probably know you're not sick. So unless they're just trying to trick you, you believe you're sick, so you rejected the null. They did not reject the null. A little bit of a weird story right there. So this one right here, it says the only way. This is false because there's 3 ways. Just to make it clear, there are 3 ways right here. This is very false. You can increase the sample size. You can increase your alpha level, which is how often you reject the null. Sample size is how much data you collect. Increase your alpha level, which means you'll make type 1s more often. More type 1s equals less type 2s. And then your effect size, you don't really control effect size, but it does impact your type 2 error rate. You don't really control it. How many things impact type 1 error? How many things impact type 1 error? There's a hint at the top of the board. How many things impact type 1 error? Be careful. You might be thinking 2, but that's not their answer. 1, you're right. Type 1 is just alpha. Your alpha level is your type 1 error rate. So you can control that, and then you also impact your type 2 when you change alpha. Type 2 is controlled by alpha, but there's other things. There's only one thing that controls type 1, and that is alpha right there, so I've got that cheat sheet up here. In business analytics presentation, we discussed how Target used data to figure out if a loyal customer is about to shop there. No, we had a much crazier story. What was the story about? Does anyone remember in the business analytics presentation? The story was about them finding out a teenage girl was pregnant. This is false. That's a really good trick. You guys are so funny in the chat. And so so Target was able to predict, and they could predict within a 2-week window if people were pregnant. They sent coupons to a family household, and then the dad called them and was like, "What the heck are you doing? Well, come on, Target, up your game." And then I've never heard that one. Great job, Evie. But we also talked about Moneyball. I think we talked about descriptive, predictive, and prescriptive analytics. And so the business analytics stuff, if you watch the business analytics lecture, you'll get them. As long as you, like, who here would have thought this question was super easy? Like, you'd look at it and be like, that's not the Target story they told. Like, you'd be like, okay, that is not the story Brian told. That is false. And just, if you don't remember me saying it, then be like, okay, then that's not in the business analytics presentation. Be like, did we talk about that? It'll be pretty obvious if you watch the lecture. If you paid attention to the lecture, you'll be like, no, Brian didn't talk about it with Target. He had a different story for Target. So I think always the business analytics ones are meant to be gimmies. If you watch the lecture, you should get it. So if you want help on the business analytics lecture, watch it at 2 times speed and just pay attention. Take some notes on it while you're watching. You'll get every business. It's not a big part of the test, so I wouldn't. If you watch the lecture once, you should be fine if you were just paying attention. That's our whole goal with it. Our whole goal is, did you pay attention? We're not trying to like turn you into a business analytics expert with that stuff. I think so it could be about Moneyball. It could be about different things. It's meant to be a very like high level question or like that everyone's going to get. Could you explain the large enough end condition real quick? Sure, let's try that real quick right here. It is in yesterday's video. I'm going to do it real quick here, Jamie. It is in yesterday's video where I went through it a little bit. The large enough end condition, I think, Walker to question 2. So let's go and talk about large enough end real quick right here. Oh, I love that video. I know that video, Lindsay. Chelsea showed me that one, I think. So, yeah, she sent me that video, and I was like, this is just too funny. That video was amazing. Reading, like, people's random questions on, like, the sites where they're asking it. That was really good. So the large enough end condition, which is part of the nearly normal, has a few ways of going through it right here. The way we go through the large enough end is we need to do 3 steps. I'm going to break down the large enough end into 3 steps right now. You ready? Here's the 3 steps to the large enough end. 1, look at the shape. So let's draw this right here. Let's write it out. I said draw, and then I'm going to write. So the first thing to do is look at shape of distribution. So we really have 3 ways to classify the shape right here. The 3 ways to classify the shape. I want people to tell me what these 3 things are, how we usually call them. See if you can get it in the chat right now as I start to draw them. So I'm a little away from the mic while I'm doing this. That's why I don't talk as much. What are the 3 shapes we generally talk about right here? Oh, that's a horrible drawing. Kind of. This is unimodal, but Okay. Kind of. Wait, there we go. Abby got it. Abby, great job right there. And so shape, center, spread are ways we talk about distributions, but this is just with the shape of the distribution. And so we have normal, we have skewed, and we have very skewed. So does that make sense, everybody? The more skewed it is will be part of the large enough n. Like when does n need to be very large? When it's more skewed. So we'll see this here in a moment. So let me see if I can. I knew that was going to happen when I did that. I knew it. I knew it. Oh, did we fix it? I think we did. We fixed it. 2. Know the sample size for the shape for the shape. So you have to know the right sample size. So what sample sizes do you need for these shapes right here? If it's normal, then you need at least what? Oh, okay, Walker, we'll do that one next. I'll put it in the video right here for you. You got it. What sample size do we need for these? Yep, you guys got it. You need 1, 25, or 100. So the more skewed it is, the larger the n needs to be. This is literally why it's called large enough n right here. So let's go back up to here, and let's put it right here. Go large enough n. Wow. There we go. So large enough n condition right here. And it's going to do the same thing to me, isn't it? Oh, it didn't. Why'd you do that before then? Number 3. So then you just see if your distribution has a large enough n. So you know the shape of your distribution, then know the sample size, and then just see if your distribution has a large enough n. So we can do one right here. We'll do Walker's question next. And we go to analyze tip amount. And then we look at this. Ooh, I'm going to say that tip amount right there is very skewed. I mean, it's got a big outlier right there. Do you think this passes? You're welcome, Jamie, right there. Who can tell me first? Let's do step 1. If you remember step 1, looking at step 1, what do we have to do? Remember what Brian just did? Brian looked at the shape of the distribution. That's right below these. Normal. Skewed. Very skewed. Okay. So everyone's saying it's very skewed in the chat. Nice job, chat, right there. Great job, Lindsay. So you notice it's very skewed. So we've identified a very skewed. Now you might say, is it very skewed or skewed? I don't know. Well, you'll see it doesn't really matter. So if it's very skewed, what sample size do we need for it to pass? If it's very skewed, what sample size do we need for it to pass? If it's very skewed, what sample size do we need for it to pass? At least 100. What is the sample size right here? Sample size is 232, so we would pass. We pass this. So this would be nearly normal by way of large enough n. This would be nearly normal by way of large enough n. What do I mean by way of? It means we're doing the nearly normal condition by doing large enough n. And what you'll notice is a big thing I want to say is it's not like you can say 10 is good for everything. You don't need at least 10 for anything or at least 25. It depends on the shape. The more skewed it is, the larger n needs to be. So how large does n need to be? The more skewed it is. We can see right here, the larger n needs to be. What does Brian have right here? Does Brian have a confidence interval for the true proportion or the, well, it says it on it, or the true mean? The answer is true mean because I'm doing tips. I thought it would just say upper and lower 95%. It does say mean right here. So it's a little bit obvious that I'm doing a confidence interval for the true mean. And, well, I guess you won't be doing as much writing on this test. I don't think we put as many tricks on that. But, yes, this is a confidence interval for the true mean because it's quantitative. Good stuff right there. Let's do Walker's question right here. I should always put up my hands that I know next segment of the video. Briefly explain why you multiply the probability by 2 for question 1, part 3. Question 1, part 3. Question 1, part 3. Where are you at? Oh, I think I know which one this is. Yes, that's what I thought it was. Okay, cool. This is a really good question. Good stuff right here. And you know what? This brings us right back to the jump output. So you know what we're going to do? So if Walker's watching this, we're going to take this right here, and we're going to put this into Word for a moment, and then we're going to do a jump output problem. So this right here, let's go grab another bit of output, and I can actually do it from the mean. So if you notice right here, this is a mean I've been using, the tip amount. And then I'm going to go here to test mean. And with test mean, we're going to enter in a hypothesized amount. And the hypothesized amount we're going to enter in is going to be, let me see here. The hypothesized amount we're going to enter in is going to be 6. 6 is going to have a t-score of about, 6 is going to have a t-score of about 2.1 and a p-value on the two-sided of about 0.038. Let's see how close it was. Oh my gosh. Okay, I like that right there. So there's the two-sided test right there, and don't worry how I figured all that out. I've just been doing these problems for way too long. If you're wondering, I'll just mention briefly, I know what the standard error is, and so I did the math for the t-statistic in my head. Because this right here, 2 times this is about 0.7. So then I chose 6 for that reason, because it's 2 standard errors above the mean. So maybe I'll show you some of this output real quick. I don't think we go that hard on the test, but that's what we want to do right there. Let's grab, first of all, this output because it's already here on the test. And let's do this. Okay. Rounds to 0.039, so I was a little bit off. If you want to catch me on that right there. Okay. So with this output, what is going on with this output? What is the hypothesized value in notation? Can anyone tell me what the hypothesized value in notation is? What in notation is the hypothesized value? I'm going to write out a formula here while you try to figure out what this value right here is. I want to know what that is in notation. I'm going to write a formula as we do this. Okay. Close, mu naught, mu naught. It is the hypothesized true mean. It is mu naught. This right here is mu naught. And P would be for proportions. Like P naught would be the hypothesized. So you're kind of right, Kim. We're very close. We would get something like this right here. And we're going to do nulls and alternatives next, I believe. Now, the alternative, I chose a two-sided, just the way I wrote the problem in my head when I gave the p-value, would be this right here. So we'll practice how to do these next. But if you notice right here, we have mu equals 6, the true mean equals 6. And if you notice, it would actually be that mu equals mu naught. So this is actually, I wouldn't write it like this, but that is mu naught right there. That is the hypothesized mean value right there. The actual estimate, what is the actual estimate? What is the actual estimate? Go over and look at your formula on the far right. The actual estimate is what? The actual estimate is what? What is the actual estimate? Someone know in the chat. I bet you guys got it. You guys are doing great. Who knows what the actual estimate is? Y bar, you're right. This is Y bar right here. Excellent job, Julio. That is Y bar. What are the degrees of freedom? Well, they're n-1. They're used for calculating the t. And so the sample size here, we can tell from the degrees of freedom that n is equal to 232 because the degrees of freedom are n-1. So if you know that this right here is this, you know what the degrees of freedom are. The degrees of freedom are there in the formula, and it's n-1 for this. And so the sample size is 232 because the degrees of freedom are 231. Does that make sense to everybody right there? The standard deviation is just going to be, let's mark this right here. This is df, and the standard deviation is s. So there, no worries. And you can see here in the output, I can show you that the standard error, we saw the standard error right here. The standard error of the mean is 0.0039. So watch this. I can take right here and do square root of 232. And I can do the standard deviation of 5.1744749 divided by that, and look what I get. I get this right here. So by taking the standard deviation and dividing by the square root of n, right here I get the standard error. And remember, I was able to use that in the output because all I did, here's what I was solving in my head for those wondering, well, how did I know the answer? This is what I was doing. I took these numbers right here, and I did a rounded version of the problem. So I basically said my sample mean is 6.7, My hypothesized is 6, and my standard error is about this. So this was about equal to 2. And as soon as I know 2, then I know I'm basically doing this graphic right here. So I drew this out. And if I'm right outside of 2, then the p-value will be a little bit less than 0.05. And so that's why I was making that guess right there, that's less than 0.05. So don't worry, you're not meant to figure those things out in your head, but if you're wondering, how did Brian do that? I kind of chose a number that would have a t-statistic close to 2. Since it's a little further out than 2, it's a little bit less than 5% of the area on the two-tailed test, and I just got lucky with my guess. So that's how I was able to guess the p-value by knowing the t-statistic, but there's my rounded version of the problem, and then these graphics right here are very important. So the test statistic is actually this right here. So there's the test statistic you're solving for, and so that is the t with the right amount of degrees of freedom, and then it also goes to this right here. That is that red line right there. So what is this p-value right here for? This is the greater than test. This is, oh my gosh, this is the does not equals test. This is the greater than test, and this is the less than. Sometimes I'm thinking about the next thing I'm going to say, and I'm like, wait a minute, didn't explain that one yet. So what do these two tests right here add up to? What do these two tests right here, what must they add up to? What do these two tests must add up to? They must add up to this, and this will answer Walker's question. Those two tests right there are above this red line and below this red line. So you're literally shading the whole curve. So they add up to 1. Then this one right here, the top one, is always what times the smallest. The top p-value is what times the smallest. The does not equals, if you look at this right here, so we're going to use rainbow pen. Space pen's better. This right here gets reflected to the other side. Double it. You're right. So we'll do it right here. So that's 2 times the smallest. And so just to show the mathematics on that, you can take the p-value right here, 0.0193, times it by 2, and there you go. That is the p-value that's 2 times the smallest. And I'm highlighting it there visually, showing you that this area right here is 0.0193, and both of these areas, which is just double this one because you're just reflecting on the other side, is 0.0386. So it's 2 times the smallest. Test will be open at midnight. Oh my gosh. Less than 9 hours away. My gosh, isn't that crazy? So that is this output right here, how to analyze it and understand what's going on with it. Good stuff on that. What was the next thing? Nulls and alternatives. Nulls and alternatives. Are you guys ready for nulls and alternatives? Yep, Katie got it. So let's do all the nulls and alternatives. Okay, so I'm going to go back to this sheet right here because I'm going to do something very important on this. I'm going to go to a new page is what I'm going to do. And let's go down and do all the nulls and alternatives on this page right here, and then we'll show off which ones we're doing. So I'm going to highlight this text and get rid of it. There we go. Okay, so the first one we're going to do right here is the null and alternative for one categorical proportion. We're going to do it for one categorical proportion. Yep, you are correct, Lindsay. Yep, and we'll do degrees of freedom in here also. So, Brian, I'm going to put degrees of freedom in this, and then I'm going to also do nulls and alternatives right here. So here's your 3 steps. This is kind of your intro to writing nulls and alternatives. This will hold true for 3 out of the 4 times we do it. This is true for 3 out of the 4 times you write nulls and alternatives. You ready? There are 3 parts to writing nulls and alternatives. The 3 parts are part 1, part 2, part 3. Part 1, part 2, part 3. Let's put the numbers. Okay. So there's some easy parts of this. We're going to do it in order for the moment, but then we'll notice what's the easy parts. Part 1 right here depends on the test you are doing. So this first part right here depends if you are doing this test, this test, this test, this test, but the last, well, not that one. Sorry, I thought it was the last one. The chi-squared doesn't match it. So we have the first one, I said there'd be 4 times. That matches what we'll do. This one, and the last one does not count as the way we do it. And so now we have to look at right there, nice job, Julio, right there, is we have to look at what are we testing. When you're testing a proportion, it's going to be P. When you're testing a mean, it's going to be mu. When you're testing 2 means, it's going to be mu1 minus mu2. So this is a huge hint right here on how to write the nulls and alternatives, because when you're testing a proportion, you're testing the proportion. When you're testing the mean, you're testing the true mean. True proportion for the first one too. When you got a population parameter, nice job, Sarah. And when you're testing two means, you have two means you're testing, two true means. So this part right here, part number 1, can only be things like P. It can only be things like mu or mu1 minus mu2. Those are the only things it can be. Those are the only things, well, in this class, you can put it, there can be sigma in there, but we're not doing that today. But in our class, these are the only 3 things it can be. It's a population parameter that we're testing, the true proportion, the true mean, the true difference between two means. And as soon as I put right here for this one, we're going to start this very first one right here. As soon as I put P inside of here, this is why I call it part 1. What am I going to put for the alternative? What am I going to put for the alternative as soon as I put P right there? Who can tell me what goes in the alternative? If I put P up there, what goes in the alternative? If I put P right there for the null, what goes to the alternative? I know what you're thinking, Brian. I know what you're thinking. What goes in spot 1 for the alternative? And Lindsay, I think you got it. P. Whatever goes here goes in the same spot. I think people are already going to the next part, because now you know for part 2, which I think Brian and other people were already getting to, part number 2 is where we put a sign. Now, what sign do we always put for the null? People know this. The null always has the this sign. The null always has the this sign. You got it. Null always has the equals. Now, the question will derive which sign we put down here. Do not think that this is the answer. This is not the answer. But we are going to put one of these 3 signs depending on what the question asks. The null always has the equal sign, and the alternative has either the greater than, less than, or not equal to, depending on which way we do our test, which relates to the output right here where we pick the greater than, less than, or not equal to. So there's the greater than, less than, or not equal to. Oh, no worries. You guys are fine. Doing an excellent job today. And so we go back to our sheet right here. I got so many sheets of them, I'm just going to lose it all. There's another null alternative. Where'd that null go? Here we go. And so last but not least, the last part of this is the hypothesized value. So what is the hypothesized proportion that we're using right here? What would be the hypothesized proportion? Does anyone know how to write the hypothesized proportion? Does anyone know how to write the hypothesized proportion? How do we write the hypothesized? And it's going to be some value. It would be like, earlier we said, like, it could be 0.5. It could be, the question could say, let's see if more than 50% of students like online learning. So we'll see. Via Zoom. So it could be, that could be the value we're testing. It'll be always known as this, though. Usually it has a little symbol next to it. Usually it's P something or mu something. And you saw it earlier in the previous problem. Usually it's P something. It is P naught. You guys like it right there. P naught. P naught. And guess what? If it goes in the 3rd position, it stays there. Now, I want to point out, I think it was other people were saying it, so Sarah was saying it. Great job, Sarah. The question could say, let's see if more than 50% of students like online learning, which means you would then do this right here, and then your alternative would be that the true proportion of students who like online learning is greater than 50%. So let's see if more than 50% of students like online learning, so we have an alternative that we're trying to see if there's evidence of, that the true proportion of students who like online learning is greater than 50%, as you can see right here. So that's how we would do the alternative right here, see if there's evidence of that. The null always has the equal sign. We start out with believing it till we have evidence of the alternative. So if you want to do one for the mean, let's do one for the mean right here. We're going to do the same steps and do it for the mean. So when you do the mean right here, we need to go get the one for the mean. It's going to be this one right here, which means we're going to test the mean. So in the first thing, if we put mu for the first thing, what will we put for the second thing? I want to see it in the chat. Who knows what I put for the first and second thing? I'm going to put mu up here in position 1. And then for the position 1 down below, I'm going to put what? Mu, you got it. And then the null always has the equal sign. Remember that. Null has the equal sign. And maybe Brian wants to see if it's not equal to a value. And I did this earlier. And then the last thing to go here is the value I'm going to test. This is the tested value. So what could we call this value? Not mu, but mu what? The hypothesized tested value goes in position 3. Is it making sense, Brian? Oh, that's a good scared face. Mu naught, you guys got it. Mu naught goes right here. And this is whatever value I am testing, mu naught. And so earlier, You saw me do 6 right here. So 6 was my hypothesized value. Just so you can see it again in the jump output, when you do your jump question and you go to test the mean, guess what it asks you? It asks you for the hypothesized mean. So if I put something ridiculous in here like 0, like people aren't tipping, you'll see that these p-values come out very low, that we have evidence that the true tip is greater than or not equal to. We have evidence for both of these. But how will we know which test to use? Will it say mean? Yep, you're right. Great question right there, Megan. Maggie, sorry about that. Maggie, we'll make you mod here, Maggie. So, and I think there's a few other people. Katie, we'll make Katie mod too. Welcome to the mod squad right here. So, go add moderator. Cool. Now, no matter what, you can't be timed out unless I demod you, but don't worry. But the question itself, like my question earlier was, let's test the tip amount that people give. So if you test the tip amount, that's quantitative. So if you look back up here at our cheat sheet from previous, these variables right here, this one is categorical, so that'd be like testing people using card and cash. This one is quantitative, like is testing the tip amount. This one is categorical quantitative, that's like let's compare tips between card and cash, because you have card and cash, and let's look at the tips. And this one right here is 2 categorical variables, so you'd need like, let's see if what gender uses what payment type more, because gender is categorical and payment type is categorical. So we go right here and we get to this one. Now this is testing the what between 2 means. I want someone to tell me this is testing the what between 2 means. Look at the equation up top. This is testing the what between 2 means. You're welcome, Maggie. Excellent questions. Keep asking questions. I'll be here for another. I got another review at 4, but I'm going to stay totally till 4. Julio, you're right. And Joel, you're right. It's testing the difference between 2 means. So when you go down here, in position 1, null always has the equal sign, so we can just leave that because the null has the equal sign. We're going to test the difference between 2 means. And here, I think, is where people get a little bit confused. On this one, we're going to assume that the difference is equal to 0. That's the value we hypothesize is true. So that actually can be called like a delta or different things, but usually we just test 0. You can test other values. We don't really do that much, but it totally can be done. You can use confidence intervals to do the test if you want. I'm waiting for a statistician to be like, yes, you should test other values. Like, just look at the confidence interval. It does the test for you. And then whatever alternative you want, once again, you can select between, I just want to show there are 3 alternatives, does not equal, greater, or less than, and that tells you which way you shade the curve. So these are your options here for the alternatives. Whichever one you want to use just depends on you, and that's got it for there. And then this one is 0. Or that doesn't look like a 0. That looks like a 0. So this is how you write the null and alternative for the 2-sample t-test, where you test the difference between means. On our test, it'll always be 0, but in technicality, you can test other values. You could always use your confidence interval to test those, because anything outside the confidence interval you can reject or not reject, Abby. If it's outside your confidence interval, can you reject it or not reject it? If it's outside your interval, so here's your interval, I'm inside the interval, and if I were to go outside of it, can you reject that value or not reject it? If it's outside your interval, you'd reject it. So if you want to test another value, you could just look at your interval, and if your interval has that value, you would believe that value, fail to reject, and not believe it like it's true, but think it's a possible value. Like, well, that could be the truth. And if it's outside your interval, you would reject it, meaning you're like, I don't think that's true. So it's like me saying to you, imagine this. Florida students decide to take our test too. Sorry, Florida students. But we look at the scores of Stats 1 students versus Florida students, and we were able to reject the null that there is no difference. Our interval, when we did, let's do this. I'm going to delete everything right here. So we're going to do a test right here. You ready? Our test is that the mean for Tennessee minus the mean for Florida is equal to 0. And what we got right here was an interval. On this test, the difference was estimated to be somewhere between 8 to 20. This is the interval we got. Here's some tricky questions. You ready? How much better on the test did Tennessee students do than Florida students? They did how many points better on the test than Florida students? Tennessee students did how many points better on the test than Florida students? I'm going to write some notation while you think about this. We can't get any more pens. So we'll go right here. This is the lower. This is the upper. No one's got the answer yet. How many points better? I'm going to interpret this interval for you. Here we go. I am 95% confident, was 95% confidence roll, that Tennessee students did between 8 to 20 points better. Brian got it. 8 to 20 points better than Florida students. I am 95% confident that Tennessee students did between 8 to 20 points better than Florida students. So we see right here that the middle of this interval is 14, which is actually where, this is interesting, I don't think a lot of people realize this, this is where y bar 1 minus y bar 2 would be. The very center of this interval would be this, because then we would do plus or minus a margin of error on this. So this is your estimate right here. It'd be 14. So what is the margin of error of this interval? If 14 is the center of the interval, and the difference we observed between Tennessee and Florida, so that's the difference we observed. We observed Tennessee students doing 14 points better. Margin of error is 6. You're exactly right. Nice job right there. Margin of error is 6. And I had another question. So Tennessee will only get a raise in their education. We'll get a raise from the federal government if there's evidence that we're doing at least 5 points better. So do you guys think there's evidence that we're doing at least 5 points better than Florida? Is there evidence that Tennessee is doing at least 5 points better than Florida? Yes or no, and why? Is there evidence that Tennessee is doing at least 5 points better than Florida? Yes. Because 5 is not contained in the interval, we would reject the value of 5. So if you did the test and you did test the value of 5, you would think that it's not equal to 5 because it's not contained in the interval. There is evidence. Yep. There's definitely evidence because it's not contained in 95% confidence interval, so we can reject the value of 5. So in truth, you can test 5. The easiest way to test it is just use the confidence interval, and if it's in your confidence interval. And that's why we show you that tests and confidence interval do the same mechanical work. If something's in the interval, like let's say Tennessee will only get a increase if there's evidence that they do more than 10 points better on average. Do you think we'd get the raise if we need evidence that we do more than 10 points better on the test in Florida? Would we get it if we need to do more than 10 points better? We did 14 points better, but do they have evidence that we're doing 10 points better? Because they took a sample of like 100 students. No, because if you look at the interval, it contains 10. So we can't reject the value of 10. We don't have evidence for more than 10. 2 hours. You get 2 hours. 2 hours for the final. Let me double check. I'm pretty sure it's 2 hours. I'll double check. I'm just afraid now when I say that. I'll double check. If we didn't put 2 hours, it should be 2 hours. Next question. I don't think it'll take 2 hours. I think it'll take most people about an hour and 20 minutes. It could take some people 2 hours. Definitely budget your time. I know long tests are not fun, but we try to utilize the time because you get 2 hours. Once again, find a quiet room. Tell everybody, hey, I'm taking a test. I can't be around. Don't come in and talk to me. There's like 50 or 60, I think. I've been looking at so much. No, and Abby, here's a big thing. Worst comes to worst, Abby. Let's say someone makes like a 60, which I think if you've been working hard and you know the concepts pretty well, if you were to make a 60, what would you make? We realize that online tests are harder, so I do like that we're doing this. If you make a 60 and you've been doing all your quizzes, then you should make probably like high 70s or almost an 80. Julio, you're awesome. Julio knows. You give that pep talk right there. My dad came over while I was taking these. Yeah, that's the thing. Like, just be like, I'm taking an exam. We'll see it during the video because we get a video of it. So don't worry. If someone walks in, you're like, hey, I'm taking an exam, and unless they're like, hey, the answer to that question is question B, be like, I mean, they shouldn't do that. Don't have them mess with you like that because we'll hear it and see it. But you know, we only go after people we think are really cheating, which could happen. I mean, people could try to cheat on this. You don't want us to flag your video and be like, hey, we think there's a problem. So yeah, just don't cheat, and you're more likely to be fine. I'm worried about not reading all the questions correctly. That could happen. It happens to me. Don't worry. Like I'll make like you guys have seen me make a mistake on my Pearson question. Once again, I think the biggest benefit of the doubt is the quizzes. So for those of you, you should just feel a sigh of relief. And finally, I'll say this. I think the exam scores will be higher than they usually are in exam 3. So I think don't be too afraid because it can easily get to you. I understand what test anxiety is like. I didn't really feel it till I took classes again, and then I was taking math classes and kind of was having a harder time, and anxiety just gets to you. I know it's hard to say just relax, and I mean telling someone to relax, if I could relax, I would. There's a lot of multiple choice, a lot of true falses. It's very similar to test 2. Very similar to test 2. So, very similar to test 2. Numeric fill in the blank, like numeric entry and stuff like that. Very, 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 very similar. If you liked test 2, and if you liked how test 2 worked with the averaging, I think you'll have the same opinion about this. So if you like test 2 and you like how it worked with the averaging, I think you'll have the same opinion about this. We have one more type of null and alternative here. One more type of null and alternative. Let's do it. The last type of null and alternative. Love test 2. Yeah, I like that right there. So let's look right here. I haven't done this one yet. I haven't seen this data. So I think it'll do it fine. And let's look at the data. Here we go. Here's the last test. Who knows? True false gets me sometimes too, Katie. Who knows how to write the null for this question? Who knows our trick for writing the null? Katie, I think you were the one who asked this. Do you know the trick for writing the null with this? When you see this output, do you know the trick for writing the null? It's a very quick trick, and if you know it, you can get the null like that. Day is independent payment method. Sarah knows it, and she did it instantaneously. Nice job, Sarah, right there. Excellent work. All we do when we see output like this, which is the last test where we have nulls and alternatives, is we take our output. Let's bring it over to Word. And go back here to Microsoft Word. Back. Where'd it go? Here we are. And so we're going to go down to here. And sure, that's not going to work. Okay. So this is the chi-squared test of independence. And we go right here and we just write independent. So all you do is just say that the two are independent of each other. Day is independent of payment method, and you could say payment method is independent of day. Either which way is fine. And then when you do the alternative, you say not. So this is all you have to do. So if you look right here, let's draw it in here. And let's go H sub O and say day is independent of payment method. That's too long. And then the alternative would be day is not independent of payment method. And the structure you're noticing right here is all we do is say X is independent of Y. X is not independent of Y. That's it. If you see this plot right here, you can just put independent, not independent between them. And the null, or excuse me, the test is the chi-squared test of independence. So all we're going to see is if the two things are independent of each other. Does this make sense to everybody? It's my favorite one to do. It doesn't use any statistical notation. Even though I love statistical notation, it's a very easy one to teach, that if you know when you see this plot, you say day is independent of payment method, day is not independent of payment method. What do you guys think? Do you guys think, I'm going to take a guess at the p-value. I didn't see it. But do you guys think the p-value will be large or small? Look at Saturday. Saturday, people are paying with cash a little bit more. This live popped up in my YouTube front page and graduated. Oh, that's so awesome. Leja, I know Leja right there. Leja, I am engaged. I think you guys were asking about that. You guys were in the room with Petrie in 474, and you guys were like, when are you going to ask her? I think you guys, yes, you guys were like, when are you going to do it? I'm moving to Texas with Chelsea, so good to see you. I was, was that when I was, kind of staying in Petrie's class to get ready to teach 474, which now I'm going to do a 474 review after this. So Texas, you go right there. We got Julio. You don't even know Julio. Who's in chat? Leja. I'm so sorry. Leja. I just had, my students know I just had surgery on my mouth. So great time of surgery too during all this stuff. But Layla, there we go, Layla. And that's when I was sitting in on Petrie's class, I believe. Can you go over the Greek letters? You got it. So it's so good to see you. No, just so good to see you too. You guys know, I'm happy to see former students. If you want to give them some words of encouragement, they have their tests starting up tonight because you know all this craziness. And I guess I'll ask real quickly, if you want to say what you're doing, you don't have to drop too many things. But I'm always glad to hear from former students and everything like that. I know let's take out our Rangers game when things start going back up right here. It's so cool. Man, and thank you for swinging by. It makes me so happy to see someone's name in the chat who I'm like, oh yeah, I remember. Of course I remember. You guys are like, when are you gonna ask her? I'm like, I'll ask her. She said yes. So that's a really good thing. Just taking my time. So that's awesome right there. It makes me smile. So it makes me smile because I have all these members of Chelsea, you guys being like, come on, Brad. It's like, I'll do it. So the Greek letters. Let's do this right here. Let's do all the Greek letters and everything. So we have right here the difference. Let's be estimator and now logistics analyst working at Tableau. Oh, that is so awesome. Well, when we do the business analytics forum again, I hope you come to it. So come to the business analytics forum whenever it's going on. And also, I'd love to hear more about Tableau. Tableau is an excellent visualization software. So all great stuff right there. That's so awesome. Thank you, Katie. So good to have you. So we just like to have a little bit of fun. And so Layla, you came at the perfect time because we just finished the chi-squared test of independence, which I'd love to see the visualization Tableau makes for that. We're still using jump. We might start using R in 201. There's things like there's GUIs for R if you know what a GUI is, graphical user interface. Of course you know. For other students who don't know, but there's GUIs that are coming out for R, and I think one of them is called like Sky or something like that. But Blue Sky, maybe something like that. But we're looking into ways that maybe we might start using that. But we're always open to new things. We want our students to be knowing about coding, knowing about software. And Petrie, of course, uses Tableau, and I need to use Tableau more. Tableau is an excellent software that a lot of companies use. Very, very popular. So with that right here, if you guys don't know about Tableau, check out Tableau. It's my plug for Tableau right there. With this right here, let's talk about these Greek letters. Why are all the pens black? What happened to this right here? Okay. So I need your guys' help right here. I need your guys' help to figure out each one of these. So we're going to put here the symbol. And then we're going to put what it is. We'll put meaning. So we've got the symbol and we've got the meaning. Spelled it right, I think. So the Greek letters, we'll start with those because that's what Abby wanted right there. The Greek letters are things like mu. So what is mu? What is mu? It's specifically it's something very specific, but what is mu related to? Love the handwriting. Thank you very much. It's the best I can do. Population mean, you are totally right. Excellent answer right there is population mean. What you'll notice about all of these, and you abbreviate it the way I was going to do it, population mean right there is mu. Now, there's another one. I'm sorry, it's not a Greek letter. P. P is going to be population proportion. So that is not a Greek letter, but it's population still. P hat is sample mean. P hat is sample proportion, and Y bar is sample mean. We'll put those up here in a second. And then we go right here, and we put sigma. Sigma is population what? Sigma is population what? Anyone know what sigma is? Sigma is population standard deviation. You're right. Nice job in the chat. Excellent work right there. And then I'm trying to think of, I guess, so that's the population size right there. I'm trying to think of, we have other Greek letters, but we really don't use them that much. We have like beta. Beta is I know you're thinking beta type 2 error, but beta is also the beta weights for regression. So that's for regression, the true coefficient of a regression, but that's not on this test. So pretend I didn't write that because that's not on this test. I'm trying to think what else is on this test right here. You know what we should do? We should write up here a sample. So even worse handwriting. So the sample, beta goes with power, you're right, but it's also used as another symbol for the truth of a coefficient or regression. Don't worry about that. Pretend I didn't say that, Abby. Beta is what goes with power on this test. Sorry, statistics ran out of symbols and had to use something twice. But beta is what goes with power. Anyone got that's some people got that. It's such a good thing, Julio. So we have right here. No, you're fine. What is the sample thing we use for mu? What is the sample version of mu? We should have showed Layla that. We'll do that right after this. What is the sample thing for mu? What is mu as a sample? Y bar. And in technicality, you could call your variable x and be x bar, and that's the sample mean of variable x. So you sometimes see things like this. This would be the sample mean of variable x. That up there is the sample mean of variable y. So all you do by putting a bar over the variable is the mean of that variable. So x bar is the mean of variable x. So you'll see it sometimes like x bar. It's like, oh, that's the mean of the x variable. And then p, what is the sample version of p? What is the sample version of P? Does anyone know? P hat, you guys got it. Nice job. What is the sample version of sigma? What is the sample version of sigma, which would be sample standard deviation? I love it. I love seeing that sticker. I should do it to mine when I go to Texas. He'll be like, "Oh, you got a T for Texas? Why is this orange? Oh, you're UT. Oh, yeah, the real University of Tennessee." So I'll tell everyone in Texas. They'll get mad at me. I'll be like, "Yeah, I work at UT." They'll be like, "Oh," I'll tell them that. I don't know. Maybe it's not best to let people think something that's not true. If you're in another state with a T, which is only Texas and Tennessee, right? I think so, right? I feel like there's a third, and then you guys will be like, "Brian, you forgot Talaska." I'm like, Talaska. Always forget Talaska. But little notes right here for the test. We've got all this good stuff. I think this is a very this is what I would call the real UT. You got it. This right here is what I would call the most important symbols on the test. I can't think of any other major ones that are super important. Of course, Z and T. I love that, Julio, standing up for us right there. And Layla, if you're here, we have the randomness button now. So Layla's going to be like, what the heck happened? We got the randomness button. We can do randomness anytime we want. So you know it's randomness right here. That's what we like. That's music right here. Awesomeness. Just let the hair go crazy. We've also got our rainbow button. Of course, we have our rainbow button where we want that rainbow happiness. So I don't know if she's still here, but we've got all that fun. But I would call this segment of the video the most important symbols for the test. It's not all the symbols, but I would say that this is like a really good version of them. The sample mean. So all you have to do is change the word right here to sample mean, and you would have these. So P hat is the sample proportion. S is the sample standard deviation. N is the sample size. So the other ones in black right there are the population, the Greek letters often, and there are other things. Like, I'm gonna draw this really quickly right here. I'm gonna erase it. Do not take notes on this. And this would be, so that'd be the population coefficient for all data, and then the sample is B. So don't take notes on that. That's not on this test. That's in 320. So just knowing the difference between the population parameter or the sample statistic. And so you notice these are right here. Let's go on this one. Maybe that makes a little more sense, and handwriting's a tiny bit better. So we have their population parameters and sample statistics. So one more try that. That's perfect. I like that one right there. What other questions are there? We got like 22 more minutes. How many people do we have watching? We had 40. I bet we're down. Do we have still 40? We probably have 20 now. If you have questions, 30. I'll take 30. That's awesome. With 28 likes, you guys are amazing. That's a really good like to viewer ratio. Thank you so much. Throw a like on the video if you want. Remember, any video you watch, if you just hit like, that's a huge help to the channel. My dream is that people all around start watching our videos. It sounds like I'm getting choked up, but it's just surgery. But my dream is that we have a bunch of people watching our videos and asking questions and swinging by to say, hey, we like that. What other questions are there? We got time easily for another one. Mara, put timestamps in the video. I'm going to try to timestamp more videos. I do want to point out, if you were here earlier and you didn't see it, I'll show you again over here that I am able to add timestamps to the videos. And so the video from yesterday, ask questions if you have them in the chat. We'll do another problem right here. We did all the different outputs today. We did all the nulls and alternatives. So in yesterday's video right here, you can literally hover over the timestamps, and you will see it says what we're doing. 7.2, you got it, Abby, you got it. So if anyone noticed, I think everyone's noticed this by now, but you can see I'm doing formula sheet review right there. So you can just hover over it. What is the formula for degrees of freedom on the two-sample t-test? That is just a complicated formula, which we will not have you memorize and we will not have you do. JUMP solves that for you. So I'll show that one real quick, but JUMP will solve that for you. So if you do a two-sample t-test, we do not make you memorize it because it's a long formula. It's just more steps than we'd want you to do. And so the degrees of freedom are going to be right here. There's the degrees of freedom, and that's found via a complicated formula. And that's the degrees of freedom for the two-sample t-test. The one-sample t-test is n-1, and then the chi-squared test of independence is rows -1 times columns -1. Can anyone tell me how many degrees of freedom are on this test right here? Can anyone tell me how many degrees of freedom are on this test? How many days of the week are there? How many of this? So it's a 7 by 2. So 7 by 2 turns into what by what? You're right. There's 6 degrees of freedom. So there's 6 degrees of freedom. We can check our work. You were right. You figured it out. Nice job. The reason being is it's a 7 by 2, which turns into a 6 times 1. Does that make sense for you right there? It's a 7 by 2, which turns into a 6 times 1. I can't do it with, I don't have enough hands to do where I usually do a 3 by 3 turns into a 2 by 2. But that's rows minus 1 times columns minus 1. 7 by 2, rows and columns. 6 by 1 is rows minus 1s times columns minus 1. And good stuff right there. Excellent work on that. We had, Abby had a question. Can you go over 7 part 2? Let's do 7 part 2 right here. 7 part 2. Where is it? Let me stop this. Doop. 7 part 2. Oh, I had it up. Where did I have it? 7 part 2. Oh, I had it up and then I closed it. Now I remember. Okay. Just closed it a moment ago. It's like, where did I put it? Okay. Part 2 and part 1, you got it. So 7 part 2 and part 1. Right here. Okay, cool. We got some jump output. You guys know I love jump output. And then when I look at this output, I see some stuff instantaneously about it. Am I testing one mean, two means, or a chi-squared test of independence? Is this one mean? Well, don't look at this. Is this one mean, two means, or a chi-squared test of independence? One mean, two means, or a chi-squared test of independence? And it kind of gives some major hints. Two means, you see the two sample t-test right up there. So we got some major hints on that. We know this is a two means test. This is a two means test. Going to print off tonight. Awesome. New formula sheet is up. New formula sheet is up on the Stat1 webpage. And maybe I'll send out an update on it. But the new formula sheet is up. Probably need to send out the update and just say it's up. But it is up on the Stat1 webpage. So this is a two sample t-test, which means we have one quantitative and one categorical. So what was my categorical variable? What was my categorical variable? It was the groups people are in. The groups people are in is the categorical variable. We might be looking at scores for these groups or something like that, but we see it's group 1, group 2, and some sort of score for them. So we have 95% confidence intervals, and it wants the margin of error. So when we get the margin of error right here, let's do this. When we get the margin of error, we have a few formulas for margin of error. Let's do our trick to remember these. If you're working the test, here's your trick. You ready? Dinner is going to cost between $20 through $30. Here's the lower, upper, and the center is some value. Can anyone in their head tell me the margin of error of $20 to $30? Can anyone in their head tell me the answer, the margin of error of $20 to $30? Can anyone in their head? You got it. It's 5. Now we have to be like, well, how can we know that? There's a lot of ways. This is a margin of error. That's another margin of error. And that's another one. So what do we see right here? We have 3 formulas. The 3 formulas are upper minus, let's try black. Upper minus center. Center minus lower. And 1/2 upper minus lower equals margin of error. Yep, Amazon shipment. So these are all the formulas with Chapter 19 homework. I think I probably don't have enough time, Jay, because I have a review at 4. Email me if you're stuck, but I do have that probably in the video. Look for the video from the last lecture I did, and you'll probably see people putting, I go through the whole homework. I still have the beard, so it'll be from last week, and you'll see like business analytics lecture. So look for that, Jay. It's the business analytics lecture, and I believe I do the whole homework. So I'm starting another review in 15 minutes. So I'll probably head off here in 10. But the business analytics lecture from last week, last Thursday, you should see me go through the whole homework at the end of it. So kind of go through the video and look and be like, he's doing the homework now. And if you're stuck, email me and I should be able to help out later. But great questions, Jay. Thank you for being here. And these are the formulas. So can anyone identify what we have up here for the question where the upper and the lower are at? You can probably see it. It says upper and lower. So now that we know the upper and the lower, we just need to do upper minus lower divided by 2. And so, awesome. You're welcome, Jay. So good to have you. So we want to do upper minus lower divided by 2. This is where it gets interesting, though. Both numbers are negative. So upper minus lower divided by 2, which is when you think about it, 30 minus 20 divided by 2 is going to be 5. What I would do is I would do 7.3752 minus 1.4648. I made them both positive just for the fun of it because it's easier to handle them when they're both positive. You can do negative 1.4684 minus a minus 7.3752. But just look at this number you found, and I've just found the what of the interval. I've just found the what of the interval. Not the margin of error. I've found the full what of the interval, how what it is. This right here is a number that tells me how far these numbers are apart. This is the full length of the interval. Does that make sense? And what do I want for the margin of error? Not the full length, but half the length. Does that make sense right there? That is half the length of the interval. And then look at it and say, okay, this goes from negative 1 to 7, about. Does 3 sound like the right amount? So to find the difference on the outputs, it's upper minus lower. That is to find the length of the interval. And so if you do this, here, let's put this number highlighted. Great question, Julio, right there. If you want to find this right here, this one right here is upper plus lower divided by 2. So that one right there is upper plus lower divided by 2. So if you think about this, we have here a negative, clear it. So this is negative, I think now, 4.42. That's negative. And then we're going to add, upper is negative 7.3752. That's negative. And then we add to it 1.4648. And so we're adding that to it. That equals this. We divide it by 2, and we get the center of the interval. Does that make sense right there? It's upper plus lower. Because think about this. The center is the middle of the interval. It's the average of the interval. So that's how you get the center of the interval right there. Exactly. Great job. So the center is the average of the two numbers. Good stuff right there. That's the middle of the interval. What was the value of the t degrees of freedom used to make the confidence interval? Now, you have to be very careful. A lot of people think that these two things are the same. These are not the same. Those are not the same right there. Those are totally different. Julio, you got it. Julio already knows how to get the answer right there. He got it. Because check it out. Let's write our formula right here. Y bar plus or minus t. This is what it wants. And so we need to put in here the standard error. Now, what we know is, I'm going to hiccup everywhere. The margin of error is equal to, we just found it a moment ago. Let's find the margin of error. The margin of error is equal to, I'm going to do it another way, 4.42 minus 1.4648. And that's the margin of error. So 2.9552. The margin of error is this right here. This is the margin of error. So since this is the margin of error, 2.9552 is equal to t times the standard error of y bar. Now all we need to do is look at our output and say, what was the standard error of y bar? It's 1.4713. And then all we do is divide t by, or we divide 2.9552 by that, and we'll get t. So all we're going to do is just do a little algebra and just take this over to this side and divide by it. So it's going to go over here. We'll do it a little bit better. It's going to go right down underneath here. And can we click it? Yeah, we probably can. Oh my gosh, we did it. Whoa, look at that. That's awesome. Okay, now it wants to grab that arrow there too. But we're able to do that, and we're able to solve for t. So I like that. I'm going to try to do that more often, trying to get better with my drawing on the screen. My handwriting will never improve, but my tricks will improve. So we take 2.9552, and then we divide that by 1.4713, and that was the t. And think about this. A 95% confidence interval has a t probably, this is not a promise, but a 95% confidence interval has a t probably very close to what if the degrees of freedom are high? 68, 95, 2, you got it. So it's no coincidence right here. But be careful, this is the t. A lot of people get confused. This is the t for the t-test. The t-test was testing to see if there was a difference, and that's a whole different t right here found the following way by taking negative 4.42 and dividing that by 1.4173 right there. And that is the t for the t-test is negative 3. So this is negative 3. The degrees of freedom I don't know how to solve for because we weren't given enough info. The p-value on the greater than does not equal as long as the degrees of freedom are higher. Probably, this is a guesstimate right here, so no one be like, how'd you know that? They're probably something like this. And would that be right? No, it's got to be a little bit bigger than that. Probably about that. These are guesses. And so those are just guesses there. What if it's low end? Then the distribution is very different. The t and the z are very different when the n is way smaller. The smaller the n, the more difference they have. So the t and the z converge towards each other, or the t converges towards the z as n gets larger. It meets it at n equals infinity, but infinity is not a real number. It's a construct. It's a theoretical value. I think that's got it. Great questions. Excellent job. Remember, if you're watching a video, throw a like on it, throw a comment. Comments and likes really help out the channel a lot. Thank you to anyone. Just think of something to put at the bottom of it. Make it sure it's relevant. Don't just be like, just put relevant things at the bottom. Check out your points. Amazing job on all the points. You're welcome, Abby. Thank you, everyone, for being here. Check your points while we're still live right here. Tons of people are getting tons of points. So great. Remember, the more you talk, the more points you get. And we're definitely using this over the summer. But you're welcome, John. Thank you so much. You guys can swing by. We might do a video game stream in honor of the semester ending. Who would watch Brian playing video games at some point? If I were to do Mario speedruns, would you watch that? Would you swing by for a Mario speedrun? Beat it in under 7 minutes, as Brian goes. Abby, you're going to get to 1,000. Mario on the weekend, maybe. Yeah. Swing by for a Mario speedrun. Maybe I'll stream for like 30 minutes if I can get the emulator working on this and get the controller working. So as long as it feels normal and it doesn't feel like if it's weird, then I don't want to play it. Like if it just doesn't work properly. I have a Nintendo and I have Mario. I just don't have the hookups to hook. I don't think I have the hookups. It's just not really possible. Well, that's got it. Let's do it. Let's play some Mario because I just want to play original Mario again. I haven't played in a while. Awesome. That's got the stream. I will see everybody later. Bye, guys.